Okay, so today we're going over the definition of derivative and the power rule. So kind of both together. But first I want to take a look at this example. We had a problem like this before, and this is one in which you need to know how to do. You definitely see something like this as particularly a multiple choice question on your AP exam. And what's so special about this question is that you have to identify that it's the definition of the derivative, or you have to identify it's the alternate definition of derivative, not that you have to actually find the limit, because, well, if we find the limit here, we get 0 over 0. That's not good. So here we go. It says the following limit represents the derivative of a function f of x at x equals c. What is f of x? So usually these problems are not telling you it's representing a definition of derivative. They're just giving you this, and you have to figure out, hey, that looks like the definition of the derivative. So what's important for you to figure out is not only f of x, but what c is. And if you look at the comparison between when you write out the definition of the derivative, and what's written here, you should be able to tell, well, the c value is 2, because it's always x plus h, okay, x is c. And in this case, it's 2. So x is c, and that is 2. And then you should notice, wait a minute, I have to plug this into the function. Well, it looks like I'm plugging 2 plus h into a function of x, and this would be the function, okay? And this is f of x. Well, if x is 2, okay, then this makes sense. This is f of x, because f of 2 is 3 times 2 to the 6, which will multiply out to be 3 times 64, and 3 times 64 turns out to be, hey, 192. Okay? Okay, so let me erase that, and we're going to come back to this. So I'm going to leave that here, and let's look at, obviously we just looked at the definition of derivative, but the power rule. When you have a function, many times your function has the variable of x, but it's also x to some power, even if it's to the first power or maybe the second power. And that's why you have to look a lot of times at how you can express your function as x to some power and maybe a coefficient, because then we can apply what is called our power rule. Okay, so I want to get rid of those examples. So we're going to assume that if f of x is x to the nth power, then we would know its difference quotient, I'm going to abbreviate, for f would be x plus h to the nth power minus x to the nth power. Okay, very similar to what we were discussing in example 1, except we're not writing limit. I'm just looking at the difference quotient and dividing by h. This would be our difference quotient. So I'm kind of developing our rule here. And to do that, I kind of have to go over something with you. Let's say we have an expression x squared minus 3 squared. Okay, so same exponents, just like you see in our difference quotient. Okay, one has an expression with x, and the other one has an expression with a constant. Okay, so x is c at some value. If we were to factor this, we'd end up with something like that. Okay, It's the difference of two perfect squares. This is x minus 3, and this is x plus 3. But I wrote it with the exponents being 2 minus 1. Okay, so we're starting with 2. And again, 2 minus 1 here. So it's a way in which we can factor the difference of two perfect squares. But now let's extend that to when our exponent is to the third power. So I'm actually going to change the x also. I'm going to make it an a. We'll talk about a and b. So let's erase. Hopefully you don't get lost. So here we're changing our exponents to 3's. And the reason for this is so we can discuss factoring that. We still have a minus b, similar to when we had like x minus 3. But in this parentheses, we have the rule it would be a squared plus ab plus b squared. Okay? And you can always find this by actually doing synthetic division or long division to figure out what that quotient is. So I bring this up because if you have a to the n minus b to the n, okay, and a to the n, I need more space, sorry. You establish that a is some factor, let's call it x plus h, then b would be just the x value. Okay. Why would b be x? Because we have a minus b here. We're talking about like a factor. So a minus b, if we do a minus b, we end up with just h. Well, why would we want just h by itself if we do a minus b? Okay. This is a way we want to factor it out. So that way we can simplify our difference quotient. Okay? So try to keep this in mind. Again, this is just deriving the power rule, like where it kind of came from. So, our difference quotient. Trying to make it smaller. We want to factor it out. We're going to leave it in terms of a and b. So we have a minus b and a to the n minus 1 plus, and we just kind of go down the row because we're factoring it out. And we end up kind of squeezing this in. This is actually an n minus 1. It does not look like that. Okay, and it looks very similar to the arrangement that we have in our second factor from when we factored out the a minus b before, and we got a squared plus ab plus b squared. So I kind of raised something more than I wanted here. Okay, last term. So b to the n minus 1. Minus. My minuses just keep going away. I apologize. Okay, so all right, that would be an expression we have in our numerator if we use the a's and b's. But remember, we established what a and b is in terms of x and h. Okay, so it's just kind of going from here. This is just an explanation to where we want to go. So this right here, our numerator, can factor out. Okay, an expression just like this. And so on. I know I'm going to run out of space. And look what happens here. Okay? That's a plus, by the way. It's x plus h minus x. So since that's x plus h minus x minus x becomes 0. Again, we get that just h. And so if we were taking the limit of this expression, okay, our h's would cancel. I'm just putting dot, dot, dot at this point. H's cancel. So we end up with whatever this expression is. Well, this expression starts where we have our variable to the n minus 1 power, okay, and then our variable to the n minus 2 power, and yet that is an h. But we can rewrite this expression, okay, and we can rewrite other expressions based on what we have there. It would be x to the n minus 2 times x. Well, same base, you add the exponents, okay? So it ends up being a definition of how many terms you have here that are really x to the n minus 1. So if you are to take the limit of that expression, okay, as h is 0, remember, yeah, you have an h is 0, you factored it out. I didn't mean to kind of erase that. Sorry, let me try to put that back in. You factored it out, okay? That means that you end up, let me erase this, you know this by now, that limit, no more h being a problem here, is this. Well, if your limit is this, you just found the derivative. This is an expression for saying the derivative, and you just found the derivative of an expression where the variable is x to some power. We call this the power rule. So this is the derivation of our power rule, and I know it's kind of lengthy and it's going to take some time to kind of absorb the factoring and what I'm writing out, but it does work out, and that's where it comes from. So if you need to, and I'm going to tell you this in class, you could kind of skip over the derivation. We're going to talk about other rules. Okay, so if you are skipping over, then you're starting on some more rules. Make sure that you have this one down. This one needs to be copied. And let me add some more. So you're going to see things kind of pop up here. So, more than once. The other rules. If you have a derivative of a constant function, because x is to 0 power, if you apply the power rule, you're going to end up with 0 as your answer all the time. So this is just something that you can memorize as well. The constant multiple rule is another one that you can kind of memorize. So it's just a number times x, so a constant times the variable. And I'm writing in such a way because I'm saying I'm taking the derivative of whatever the variable is with respect to x. If it is x, then you don't have to actually write the notation. So this becomes d over dx of cx equals c. So it's just really a small introduction, this one right here, of what you may see in the future. But you can memorize this for now. So we have an example here, and I'm actually going to go back to example 1 as well. So let's call this example 2. In example 2, I gave just one problem, and believe it or not, I accidentally am showing you what I'm going to go over tomorrow, the sum and difference rule. Okay, so that means that I can take the derivative of each term all together at once, but here today I'm just going to kind of break up. So it says, find the derivative of p with respect to t. So that means that our variable should be t in our equation for p, and it is. So if p is t to the third power plus 6t squared minus 5/3 t plus 16. So here we go. You're going to take the derivative with respect to t of p. You're doing it to the left side of the equation and all the terms on the right side of the equation. And I'm going to run out of space quickly. So bear with me. Minus. Plus. Okay. So this together is going to be dp over dt, multiplying it. And that's what you needed to find. So we already know that that's what it's going to equal. Over here, this is our power rule. So it's going to be 3t squared, okay, because if we apply our power rule, okay, you bring the nth power in front of your variable and you do minus 1 to your exponent. Now for this one, you can take your constant out, or you can kind of apply your constant multiple rule. That means that that's going to stay there as long as there's a variable next to it. So I'm going to have 12, okay, t to the first, because if my variable stays there and I move the second power over to the front, I'm multiplying them, just like I multiplied over here. And 2 minus 1 is 1. You don't have to write the 1, so I can kind of cross that out there. But you know that already. If it's the first power, you don't need to write that as your final answer. Now, over here. Okay, this is where you're multiplying a constant to a variable, similar to what I was explaining in the last term. You just kind of keep it there. And t to the first minus 1, first minus 1, 1 minus 1 is 0, t to the 0 power is 1. So that's how we end up with 5/3. I just want to apologize. There was a minus sign back here. You were subtracting this. So let me make sure that I show I'm subtracting that answer. And last but not least, this is where we're taking derivative of constant. This is 0, okay? So if that's 0, I don't need to write anything. This is my final answer. Okay, so now you saw that I took the derivative of each term of my function, and my function was p of t. And example 1 is still up there. You're probably wondering, why in the world is it still there? I'm going to go back to it. Okay. So when you see a problem just like this by itself, no other directions, and you know you can't figure out its limit by any other means that we have gone over with other limit problems, you should be able to identify if it is the definition of derivative or the alternate definition of derivative. Since we already identified its definition of derivative and we see that f of x is 3x to 6, okay, and that x was supposed to be 2, what this is asking, since it's the definition of the derivative, is to find the derivative, another notation for derivative, and we can use the power rule here to find the derivative and then evaluate it, always substitute last, where x is 2. So if you're given this as a multiple choice question, this will work out to be 576. You would pick that choice. Okay, no other choice. Now you know how to actually complete and finish those types of problems. Okay, what it's asking for is the derivative because it's the definition of the derivative. What you need to do is use your definition of the derivative, your knowledge of using that for a while now, to identify your function and the x value. And just simply do the power rule or whatever rules you need to find the answer. So that's it. We're done for today. Good luck.